Okay, thank you very much. So, okay, I should say that as everyone, but that's true that I'm very impressed by all the things we have seen until now. Okay, we just think about what we should know and what we should discover, and there is so many. Every talk is ringing some bells everywhere. So, okay, I hope that this one will also do something like that for you. Okay, so we have tried to do an introduction and divided the time in two. So this is a very huge topic. So, okay, it will not be exhaustive at all. I will try to find some, I will focus on shapes, on shape space, and Xavier will focus on on the geometric part. So, I will try to give some basic idea about, I think, the core ingredient of shape spaces. And one is, shape space is usually a quotient space. Another one is that we have the space in many situations, in particular the situation we are both interested in, which is medical imaging. The ambient space, the shapes are living somewhere, not just like that, are not abstract space, they're living in ambient space. And the action of the deformation of the ambient space play an important role, so that will be the second part. And I will give you some idea about how we deal with this geodesic shooting, which is really an ingredient which is really important when we want to do statistics on shapes. Will be enough to start the process of doing statistics on shapes. So, and Xavier will start with simple statistic on Riemannian manifold, because we will build some Riemannian manifold, and say something about more, going beyond just computing the mean. For instance, what is the mean of shape on a shape manifold? So, talking about PCA, and we'll give some kind of new perspective and open problem at the end. So that's program today. So let's start with shape spaces. And I like to start with, first, this picture, just to show that when you have medical images, or when you want to study shapes, usually you could have something which is like that. This is images. So you have images. And so you could say, here. So if I use this, So to have the laser, this is like that. Okay. So we can have images like that. So this looks like a functional space. Or you could say you could segment a substructure like that, and you can have a surface. You can have a bunch of surface, which is internal structure in the brain here. So that could be a shape, and you could have something more. There is a lot of activity into DTI, which is diffusion tensor imaging, to have the connection, to know the connection between different parts of the brain. So you could have picture like that, or much more crazy than that, where you have trajectories of you run a trajectography algorithm, and you get a lot of curves like that. So you have all that. It should be a shape first. Okay, and we'd like to work with this unconventional data sets and objects, so that's clear that in that situation there is a central place of geometry. For instance, there is a thing that in 3D medical imaging we have different shapes that do not intersect usually. And you could think about different versions of this shape when you have different patients, but they will not have intersections. So you could say that there is some kind of diffeomorphism action behind that. And so we need high-level representation. So we have images, basically, like this. We could have landmark. You put points on, you have 2D images, and you say, I will select point like that. You could have submanifolds. You could have tensor fields, like that. You have many different things. Okay. So when you say what is a shape space, in fact, I think the shape space basically is the idea not to consider just one shape, but to put shape together and to consider an ensemble of shape and to think about the structure you have. That's a basic idea, but that's not enough. So you can start with this idea, and this idea is coming from the work, the beautiful work of Kendall, which is to say that the idea is to filter out effect resulting from translation, because sometimes translation is annoying. You don't want to think about translation. It's just nuisance parameter. Rotation and change of scale. So you could say that I would like to think about shape up to translation, rotation, scale, and the shape can be just what is left. So this is a quote from famous quote from David Kendall. Okay, so if we start with this idea, let's say we start with this idea. So what we have? In fact, we could say, okay, we have a group action on a set X, which is, okay, all the basic, if we think about the Kendall shape space, you could think about triangles. I will show you this example. But can be some abstract set. You have a group action on this set. So you have a mapping from G cross X to X. This is a group action. And so you could say I have a quotient. And the quotient will be my shape space. So a shape is an orbit. An orbit. So you have your basic triangle and all the version of that triangle up to rotation, translation, and scale. Okay? So you have very simple, it's just an exercise, but it will play a very important role, is that if you have a metric on that space, and now you have an action which is acting isometrically on X, it means you conserve the distance. It means you have X, you have the distance between X and X primes, these two pre-shape, you can say that. You measure the distance, you have a metric distance, and if you act simultaneously by the same element G on X and X prime, you conserve the distance. Okay, if you have that, then you can compute a new distance, which is a quotient distance, by just computing, so this is equivalent class, this is an orbit, so you compute the distance between the two orbits by just minimizing the distance between X and X prime for X in M and X prime in N prime. Okay? So that's usually not, that satisfies the triangle inequality, the symmetry, obviously, and this is a pseudo distance, and this is a distance if the orbits are closed, so if the action is continuous. So you need very few things to have this kind of construction. Okay, and so you can think that in fact, if we want to have a metric space for the shape quotient space, we need to have this isometric action, and you could say that's the important thing. Okay, so what is a Kendall? Oh, interesting. What is a Kendall shape space? So the idea is you have Kendall shape space. You can think about collection of points like that. So you have 1, 2, 3, 4, 5, and this is this collection. This is landmarks. We call it landmarks, but you have label on that. So here you have K equal 5 landmark in a dimension M equal 2. Okay. So from a general point of view, you have this situation here. So you have X, which is this product, and you remove the diagonal. You don't want to have all the points we are at the same place. You want to avoid that. Okay? Now, you will factor out, this is the construction of Kendall. You factor out the translation and scale, but what? By some kind of standardization. So you just remove the barycenter. So you center your shape. And now you have a scale, interesting scale. You estimate the scale by computing this is some kind of variance estimate. So this is a standard deviation. So it's some kind of estimation of the size of your shape, and you divide it by that. So now you're invariant to scaling. So this is your pre-shape. And that's easy to check that you sum, you are in a sphere here. Oh, yes, I should remove this. But OK, you are in a sphere. Now, you equip this pre-shaped space with the Riemannian distance, which is induced by the ambient Euclidean space. And clearly, this is invariant under the action of a rotation. And so, if you rotate all the points, if you have two such, okay, now if you want to understand what is this isometric action, it means that if you have two different shapes like that, just to be as concrete as I can, so you have this shape and this one. Now that's clear, if you compute the distance between the two and you rotate all simultaneously both of them, you will not change the distance. Okay, and so you divide by, you factorize rotation by dividing by the group of rotation, by the rotation group. And so since this action is in isometry, you get a distance. And so what's that shape? So in fact, what you get in this situation, you get this very interesting space where, in fact, the space you have is, in fact, like a sphere. It's exactly isometric to a sphere, to this sphere, two-dimensional sphere in R3. So in the case of triangle, and you see here, that's interesting to see that, oh, sorry. What's going on? So what you see here is that you get the funny thing is that on that sphere you have all the triangles up to rotation scale. So you see that you have the equilateral triangle on the top, and you have the other by just a reflection. And on what you see that in the equator you have all the degenerated triangles. And now here's the geodesic. When you move, when you want to compute the distance between two triangles in that space, you just compute the Euclidean distance. You have the Riemannian distance induced on that on that sphere. Okay, so you could say now, in fact, this. And that's very interesting because when you want to, when you don't want, you are not interested in that rotation and translation, that's a nice way to do. Because you could have another solution which could be, you have a triangle. If you start with a triangle, you could say, oh, okay, I don't need to have all this construction. What I can do is just, I will fix A, B, C. I will say that A will be at a given location. A, B, C, and I will just standardize in the way that I will say AC, the length between A and C will equal to 1. And now I have just one solution for B, and that's clear that I have just two parameters, so 2 degrees of freedom. But you see, if you do that, that's the engineer way to do. But if you do that, you see that's not interesting because you have chosen this point, and if you do another convention, you will get some different statistics. So that's very important to be able to do that in that situation. So it's very powerful and very interesting. And there is a full school, which is the geometric morphometric, which is just behind this idea.
Sorry, what are you exactly representing here? This is the quotient that you want to represent?
Yeah, here this is, yes. So what you have, each triangle is represents an equivalent class. So this is a quotient space. The space has been quotient. Yeah, but sphere, but in high dimensional space, because you represent yeah, okay, you're right. There is something which is misleading here. Is that you represent, you have, when I say x1, this is a position in Rm. So now if you represent x1, x2, xk, now you get a vector in high dimension. And so this scaling means that when first you remove the barycenter, after you scale, so now the sum of the square of all of that is equal to 1. So you are in a sphere of high dimension. So it was a sphere. Yeah?
In the South Pole, you have also a
Yeah, yeah. But the other one, you flipped. You flipped. So that's very interesting to look at that thing. So that's smooth. Okay, so you have different shape like that. But in fact, okay, that's interesting, and I will not enter to this, but you can think that, in fact, the dimension is related to the stabilizer. You know, you need to know the stabilizer of a shape, which is just the G and if you change the dimension of that, you can have some, at some point, you can have some different dimension of that. So here, in fact, in this situation, there is no singularity, but you could have. So there are interesting spaces, and this is not so easy to work on that. And so, I'm doing just a free advertisement for Jan Dryden, which is and Kenti Mardiar and Bookstein and an English school, which is working very hard on that. And so you have 2 books, and you have a recent release. So we have a lot about this, a lot of interesting things about just what you can do with this kind of idea.
Excuse me.
Yeah?
Can we have here some space in which we measure the distance, both triangles and rectangles?
Oh, yeah, that would be interesting. Yeah. So, but like this, I think you cannot do it. Yeah. Yeah. Okay. Here you have, okay, you could say now, okay, the thing is that you could say, in fact, we will do this more or less immediately in a sense. You could say, I just need to increase the number of points. Now it's discrete, and I could say I could have a rectangle, and I could have something, and so. But now this is the discretization of something which is continuous, and you can think about, do I have a limit of these kind of things? So, good question. So, in fact, we will do something like that. So we can think about the example of smooth immersed closed curve. So now, okay, there is a lot of different kind of thing like that. So I will say just a curve like that, a continuous curve. But I have a parametrization, so I know how I go around that curve. Because this is a function from S1 to RD. And so I have the convention that the speed is strictly positive. So I should continuously move on this. But I do not allow, no, here there is no more restriction. But in some situation, we may want to avoid this. I will explain this why. Okay, so now for this, you can think about the infinite dimensional. So this is the X. So the tangent space is just a small variation of a curve. So this is, you could say, you can start with a smooth, this is just a list of vectors along the shape. So any element on that space. And now if you think about what could be a metric, because we want to build Riemannian structure on this. Okay, you have zoology, you have a lot of different metrics you can think about, but the thing is that, so it started with Younes and Mumford and Michar and a lot of people working on this. Just to think about people working on shape space, but there is many other fields, you have things like that. So you can think about Sobolev type metric, where you need to have something that's clear that from the construction you will need something to be invariant. You want to have something which is invariant with reparametrization. We guess we need that. Okay, so you could have something which is very simple. So ds is the arc length part. And okay, the simplest thing would be just to take the L2. So h and k, this is vector along the curve, and this is just the L2 norm. Okay, so we can think about that. We can put derivative, higher derivative, and so on. So we have some kind of Sobolev. We could change things which have something which is about tension and bending. So we could look at things which are tangent. There's a lot of variation and a lot of interesting things. And Alice will talk about this, some of this Sobolev metric in his talk. And so now, if you make sensible choice, you have, that's not hard to have something which is invariant to reparametrization. And so you can quotient this. And thus you have, if you do that, you work on shape in a regular sense. It means now the nuisance parameter is not to rotate, to translate this. This is a reparametrization. So This is an action on the right. So previously we have an action on the left. We move by rotation. Now we have an action on the right. But it's the same idea. So we have quotient, but that's different quotient. We have to be cautious about quotient. Okay, so here there is a lot of work which has been done by especially Mumford and Michor and a student, Martin Burris, and a lot of students to understand this kind of shape. So what I can say is that the first surprise was if you take the L2 norm, now you say you have a space and you have defined a Romanian metric, which is a smooth Romanian weak, but okay, a Romanian metric on that space. But now if you want to compute the distance, Romanian distance between two different shapes, and you compute the infimum, what you get is that the distance is 0. So this is typically a phenomenon you have in dimension, in infinite dimension, you have not in finite dimension. So starting from that, in fact, you could say, okay, I will not take the L2, but maybe I will do some kind of conformal transformation of this and put in front of it a scalar with a number which depends on the curvature. And this is what Mumford and Michor, what they did. And okay, it can be much better. So there is a lot of interesting situation you can do. In fact, it's to compute curvature. So I will get our reference at the end to compute curvature in that space. That's a very, very hard job. We have some situations, there is some few hints, but there is a full zoology. The thing is that if you want to compute, okay, the geodesic on this, you had to take the variation with respect to the metric. And that's practically, that's very interesting object, but practically that's still hard to use, except in some precise situation you will see later. So now I will choose another idea, and so the other idea is to use diffeomorphic transformation. So this comes from Darcy Thompson. So now you think about shape. Shape is, you could say, shape is not what is left before, after when you remove rotation, translation, and scaling, but a shape is something you can deform, something you can act on it by diffeomorphism. So that's another idea. A shape is something deformable. And so this is the idea of Darcy Thompson, and it has a very clever idea in the sense that each shape is very complex in a sense. If you want to describe one of these shapes, you have to describe everything. And if you want to describe another shape, you have to describe everything, this one. But if you think about the transformation, the transport, in fact, the transport can be, the deformation can be quite simple. So, in fact, you have that point, but maybe the space is simpler than it looks like at the beginning. So the idea is now to think about, to put a metric on the deformation to start with that point. Okay, so I need 5 minutes, so I need to go faster. So the idea of deformable, this is the full idea of deformable template. So here we'll say that the shape space will be what? Will be the orbit of under the action of a very big group, the group of deformations. It will be the group of diffeomorphisms. So you could say that's a different idea. That's just now this will be an homogeneous space. And so what I say is that you can act on, using deformation, you can act on landmarks, manifold, on images, on vector field, on currents. Currents are very important to represent shape. I will not have time to say that, but we have a talk tomorrow showing that, in fact, to represent a shape as a current is very good, and it's not hard at all to work to transport it by using diffeomorphisms. Okay, so the second idea is to put the metric on the group, because this is more simple. A group can be smooth, it can be, okay, you can hope that this is a D group, usually it's not, but. Because if you specify the metric at the identity, you specify the metric everywhere, so you have not to decide at every point what the metric will be. And now the thing is that you think that if you have a right invariant metric, you can define a metric on the orbit like that. The distance between M0 and M1 will be the infimum of the distance between the identity and G for all the transformation. It's a deformation course. You can just that. Okay? But in fact, you could say that's a different idea. But this is, again, the same trick. But the thing is that what we have here, that's another very simple thing, is that if you have homogeneous space, and if you look at the stabilizer of G, what you get of an element M, so you have, in fact, you have an action like that. And so if you say you have a group which is H here, and now G will be X, so you have again this. And so if you have now on X, which is G, you have a distance which is H invariant, you will be able to build something on the quotient of this, which is what? Which is just this over G and 0. And this is a simple, well-known exercise to show that this is just M. So you will define a metric on M. So in fact, what you need is just to have a metric which is invariant with respect to H. But if you are fully right invariant, you don't need to know. It will work every time. And that's okay. I have not so much time, but that's a key idea because we will, it means that you can build a lot of different shape space. And when you change the discretization, the metric comes from the same thing. So you can have inductive limit if you want, and you have coherent. It's not like that. You have a shape space like this, you build another one, you have different discretization, and now you don't know what are the relation between the different shape space. Okay, so I see that Xavier is wanted to have time to speak. Okay, so what is the construction? I will skip that. To have the construction of a right invariant metric on a group, you just need to integrate flows. And so you get at the end, you have to minimize this kind of formula. You have to minimize the V will be a time-dependent vector field, and the metric, the right invariant metric, the metric, this metric will define the metric at the on the tangent space at the identity for the group G. And by right invariant, you see that this is exactly the formula. So we recognize something which looks like a transport, but you have no mass term here because this is just a space you have moving. So there is something which is certainly that. Okay. So in fact, the cool thing is that if you start from a Hilbert space, the Hilbert space will represent the tangent space as the identity for the group of diffeomorphism. It will not be a Lie group, which is continuously embedding in C01. It's meaning control. They have enough regularity. This is a regularity assertion. Now you will get, by just integrating all that flow, you will get a group which is a complete metric space. You have geodesic between any two. You have something which is really, really cool and smooth, even if this group is not a Lie algebra, and this is you could say this is some kind of completion of a smooth Lie group. Okay, I will skip this. We have nice, just an example of the idea. Okay, so here I need to go here. Just to have a sphere. So now this is a geodesic between two balls. We are in 3D, and I just want to compute the geodesic between these two C, and I need to define a metric. My metric, I will use a kernel metric. So I have no time to speak about kernel, but the kernel metric this is a kernel of your, you start with a Hilbert space, which is a reproducible Hilbert space. And so you have a kernel, K, which is, in fact, you have your mapping. Between the vector space and the dual space, and we have K, which is the inverse mapping, which gives you the kernel. So the metric is given by this. Okay, so this is it can be a differential operator, it can be anything here. Okay, and so here this is a Gaussian kernel, and so sigma is a scale, this kind of scale you have. And so just to see one of this. Okay, so you transport, and you see I have chosen the sphere is 1, I have chosen the scale which is small, and so you see that you have this effect, which is the thing with curvature, and everything is contracting because they want to move together. So it's not like optimal transport in a sense, because you see, okay, now if you change the scale, bigger. Now it's becoming much more like a translation. Okay, you can do a sphere. I just show you, just now we have the idea that we have always a geodetic on the shape space, and you can lift it as a geodetic on the group of diffeomorphisms. So this is the... Okay, here this is not a very fancy metric. So, and so you will, I don't know if you can see the grid, but you see that you have a grid which is below everything here. Okay, this is a completely stupid matching. It's absolutely no sense, you know, from medical point of view. You should not do, because, okay, there is some constraint about this. Okay, and just to show you something more fancy. Okay, here you have a diffeomorphism. You have a full 3D diffeomorphism transforming the sphere on the rabbit. And you could say, how can you do that, in fact? Because now you get two meshes, and you have not the same number of points. So how you can do that? Okay, there is a trick. There is a thing. If you want to know how I do that, I will explain you at the end. I think that Stanley will explain also. Okay. So, Stephanie, I should stop right now?
5 minutes earlier.
5 minutes? Oh, okay. So the thing is that there is something which is very important, is that if you want to understand how you can do such things for real, with real object and nodes and so on, okay, you have to understand the exponential mapping. This will be the central tool for all the talk of Xavier. So here we have this manifold, and we have the normal coordinate. This is just a geodetic mapping. So you have this shooting. Very simple idea. Okay, but when you want to solve these geodetic equations, that's going to be quite hard. So the thing is that, in fact, because of this right invariance, what's going on? Why I have? Oh, yeah. In fact, if you look at our problem, this is optimal control problem, which is not so hard. In fact, you have to go from M to M prime by a flow, and you have to minimize this Lagrangian, which is you have a right invariance. And in fact, you usually have to add a term which is rho of M1, which is M1 is, you know what you have. You have a trajectory. Here you go from M0 to M1. You have a target. And the find that you are close to the target you will evaluate how close you are to the target looking at rho of M1. And I have to minimize this under a dynamic constraint. So the dynamic constraint is given by the infinitesimal action. So you have a Hamiltonian here, and you can define everything on it. So after you can use the usual maximum Portier-Hagging principle. And in fact, what you get is that if your shape, even if you work with diffeomorphism, if you act on something which is discrete, points, or more funny things, but discrete, in fact, you have a reduction principle, which has been explained by François Gabelmaz in just half a line in his talk. So I think that if you remember what he said, you understand that in fact you have a reduction and you have momenta. And so in fact, the thing is that in shape spaces we work with all these momenta, which is in fact a way to reduce the work with diffeomorphism, but reducing in finite dimension. Okay. So I will stop here. I would just want to say that in fact you can have, using this idea, you can have much more funny, a lot of funny spaces. You can try to look at images and to have a richer, here I have a richer action, which is not the group of diffeomorphism, but also a change of gray level. So this is the same thing, you have metamorphosis. You can also think about shape space like that, where you have shape, but you have also a structure, a function of it. So what could be things like that? And you can think about also having some metric we are more sophisticated, and I'm sure that Xavier will, Xavier, I will be also like that. I will be just looking at your time. Okay, and so if you want to know more about that, you will ask question at the end. Okay. Thank you, Xavier. That's you.
Thank you, Alain, for the introduction on the shape spaces. So now the idea is that I'm going to talk about how we do statistics on these shape spaces. So we have already, some kind of spaces. They are mostly Riemannian, and that's what I'm going to describe. Let's assume we have a Riemannian space. How can we do some? So when I state statistics, you will see that it will remain very, very simple, but we are in nonlinear spaces. So the basic tools hopefully were presented yesterday in the talk about machine learning. So I can maybe speed up a little bit. So we have the geodesics. From the geodesics, we can have the exponential map, which is mapping each tangent vector to a point on the manifold. And we need also to have the log map to have the inverse problem from 2 points, what is the initial vector to shoot. And from that, we have at each point, we can have a chart of the manifold which is covering almost everything except the cut locus. And well, if the manifold is geodesically complete. So I put that in bold because that's one of the key things. We are almost always using the fact that the manifold is geodesically complete and in the statistical results, and that's one of the things that we don't know much how to. We are not sure how to extend the statistics if it's not. So once we have the X and log, we can rephrase quite a lot of the Euclidean operation by rethinking what is the difference between points. That's a vector that allows to shoot from one point to another. What's the addition? We can't add point, but we can add a vector to a point if they have the same foot. So we think for engineers, I'm usually explaining that we have vectors with the foot. They are attached at some point. And then we can do gradient descent, where the gradient is obviously the Riemannian gradient that take into account the metric here. So that's the basic tool for computing. But now if we want to do statistics, we need to have densities. So we can try to define densities on, for instance, an embedded manifold, but we can see that it's depending on the chart. So we need to actually use the reference measure, which is the Riemannian measure, to do that. That's quite easy. It's just can be computed in any chart. So so I think I'm gonna maybe take my computer because, sorry, Mac is not so happy with the formulas. Okay, so what I wanted to say is that if we want to, the first thing we're doing when we're doing statistics is taking expectation. And what we can do in a manifold is take the expectation of a function from the manifold. So if we assume that we have a random variable in a manifold, let's say with a density, we can take the expectation of a function from the manifold to a vector space using the integral. But the integral is a linear operator, so we can't define the central point of the distribution as an expectation from a manifold to a manifold. This would be a nonlinear integral, and that's not possible. So what we can do, however, is take the expectation of the square distance. This is the variance. We can also take the expectation of log of the probability, and that's the information. And to define the mean value, we have to change the definition. And what Fréchet proposed for metric spaces is to take a property of the expectation, which is that it minimizes the variance, and to take that as the new definition. And that's working in our Riemannian spaces. So we can minimize the variance. And here I just introduced two types of notations. These are the moments that we can define on the manifold as fields. So we can define the tangent mean field here, or the covariance field. That can be defined at all the points. If we have a density, or if we have a discrete measure, it can be defined everywhere except at the cut locus of the points that we have. And so now if we look at this variance, if we take the gradient of that, where we can show that the minima, the critical point, they satisfy this equation, which is another way to define the mean, which is an exponential barycenter. So the idea here is that if I am at the mean value and I'm lifting all the data in the tangent space, now if I'm looking around and integrate the tangent vector to shoot at all points with the density, then the mean is 0. So it means that I am optimally centered with respect to the different elements. So these are the zeros. So we can define the exponential barycenter as the zeros of this tangent mean field here. Okay, and the covariance matrix, usually we take it at the mean value, but it can be defined at all of the points. So this is a way also to create fields of interest, geometric fields on manifolds, which are of interest for statistics. Okay, so now just a few remarks on the mean value, because there's quite a few use of this tool in different fields. So in the domain we use to call the mean value the Fréchet mean or the Karcher mean, and more recently we also call the exponential barycenters. So Fréchet introduced the notion in 44, but that was really in a statistical sense. Now the idea that in a connected manifold with negative curvature, there was only one minimum of the variance, that was already known by other people. But if we look at the book or the article of Cartan, that was just used in the middle of something else, not for statistical purposes. And the other thing is it was studied in many other domains where uniqueness was assumed. So it was also called the Riemannian barycenter or the Riemannian center of mass. But what I don't like here is the Riemannian center of mass. It should be the set of Riemannian center of masses. Because when we are in positively curved manifolds, most of the time we don't have uniqueness. So that's one of the key features. If in many of the spaces that we deal with, there is not a unique mean. So the convention that we have now is to call the Fréchet mean the set of absolute maxima. The Karcher mean would be the set of local maxima, and the exponential barycenters would be the critical points of the variance. So now the uniqueness can be ensured if we are in this type of conditions. So there was this was worked out by Karcher, very well explained in the almost the book of Buser and Karcher, revised by Afsari, by Lé and Marc Arnaudon for the p-means. So basically the idea is that if we are in a geodesic ball which is sufficiently small, and sufficiently small, there's two arguments. One is sufficiently small with respect to the curvature, but also at least maximum half of the distance to the cut locus. If you have topological constraint, then this is also restricting the domain in which you have uniqueness. So in these conditions, you have uniqueness for quite at least the two mean. Now, another remark of Marc Arnaudon is that in practice, when we have an empirical distribution with points, the mean is almost surely unique. So the absolute minimum, at least, is almost surely unique. Now, if we take the local minima, they're not unique anymore. So in practice, we might still work with that. Okay, so to work with that, we need to have algorithms. So one of the earlier algorithms is the Karcher flow. So we basically take the gradient of our square distance and we try to follow that. So the usual algorithm, and the one I'm almost always using, is this one with epsilon equal 1. In most of the cases it works, but it can fail. And for instance, in SPD matrices with the affine invariant metric or the canonical metric which gives a real negative curvature to this manifold, there are examples where it diverges. So it needs to be corrected by the curvature to really converge. So there's a few papers that I listed here to look at the bounds on that, and there's quite a lot of work now on the incremental mean, the idea being that instead of taking all the points, computing the gradient, and then iterating the gradient, we can take 2 points, compute the mean, then take a third point and shoot just 1/3 along the geodesic and iterate the mean like that with different points. And if we continue, or if we reshuffle the points, then this is converging. If we do not reshuffle the points, then we do not end up, if we just use one pass with the points like that, we do not end up at the minimum or the exact Fréchet mean. The difference is really given by the curvature as it can be felt by the distribution. And of course, there are also stochastic versions that were developed by Marc Arnaudon as well, where if you have here a stochastic variable and then you select stochastically also the point, then you can have convergence guaranteed in practice. Okay, going backwards. Now, if we want to do more interesting statistics, what we can do is, or what we need is some type of distributions. So, of course, what we need is the Gaussian distribution. And the idea for the Gaussian distribution is, so there's the idea of using the heat kernel, but the problem is that there is a complex time dependency. So in terms of statistics, that's a problem because usually we don't have any idea of how long is the diffusion time. So we can have also, there's quite a lot of examples of wrap distributions. So you put a distribution, Gaussian distribution in the tangent space, but if you are on the circle, then you have to wrap the distribution when you're arriving at the cut locus. So another definition, which is, I believe, a bit more interesting, is the maximal entropy knowing the mean and the covariance matrix. So that's what Frédéric Barbaresco presented. And so we can show that actually it always has this form in the tangent space, in the normal coordinate system at the tangent space. And it turns out that, well, the tangent space at the mean, it turns out that for symmetric spaces, beta equals 0, and we can have Taylor expansions of the parameters here. And here the concentration, I don't want to call that exactly the precision matrix, because as you see, this is not exactly not just the inverse of the covariance matrix. There's a correction term for the curvature. So that's what I call the concentration matrix rather than the precision matrix. And then we can do also Mahalanobis distance. So it's basically just rescaling the distance by the inverse of the covariance matrix. So here it's not the concentration, it's really the inverse of the covariance matrix. And it turns out, very surprisingly, that the expectation of that stuff for any distribution is the dimension of the space. So there's still seems to be some interesting stuff to do, and we can design or derive what is the approximate distribution. It turns out that it's quite a good approximation of the chi-square distribution if the variable is Gaussian in the Gaussian case. Okay, so just an example of the type of statistics we can do. Here, this is an example of statistics on the spine. So what has been done is there's images. On these images, there are points which were carefully pointed by the radiologist, and the position and orientation of each of the vertebrae was reconstructed in 3D. And from these 3D points, they tried to do PCA, and then they didn't find, well, they need a lot of modes to describe the distribution. And, well, if you think about the spine, especially in scoliosis, you can have people like that, so you have huge displacement between the point position. So what's more interesting is the articulated motion of the spine. So what we did is to encode the relative position and orientation of the different vertebrae. So it means that we have a rigid body transformation between at each of the joint here. And now we have to do statistics on the Euclidean group to the power 16. And this is the mean value that we find here. Oops. And these are the first modes of variation. So we compute the mean value, we compute the covariance matrix, we diagonalize the covariance matrix, and this is what's happening if we follow a geodesic along, well, from -1 to +1, or I think it's -2 to +2 sigma, along the first mode, the second mode, the third mode, the fourth one. And what you can see is the first mode is basically growing, And this was a study about childs between teenagers, so that's normal. And what you can see is there is an increase of the scoliosis with age. And that's known, it's about 1 degree per year if you do nothing. Now the two other modes, these are vibrating modes of a rope. That's exactly the first modes of deformation of any articulated or a line. And then the third mode is interesting because we capture what is the lordosis. It's the curvature here, and you see often the elderly are like that, and then they are trying to have the head which stay horizontal. So there is a big connection between the position orientation, well, not the position, but the orientation of the vertebra on top and with everything else in the spine. So that's the type of example where we can do statistics on objects, on geometric objects. Now the second point that I wanted to show is, so what's happening in a bit more complex setup. What I showed here with the spine is you have things which are, well, once we have the correct geometric formulation for our spine, all the data are quite concentrated. So we can do the Gaussian assumption. Now if you take population of images like that or population of shapes, they might have a huge distribution in your manifold. And if we want to analyze what's happening, what we want is to have subspaces in which we can have low dimensional representation of our data. However, we are starting with data which live in a manifold. So we don't want to use the usual machine learning algorithm where you throw everything in a Hilbert space that does not respect your initial constraint. What we want is to have a submanifold of our original manifold. Okay? So what we just have done previously was to say I'm computing the mean, I'm developing everything in the tangent space, and trying to explain the covariance matrix. So in order to have distributions which are larger, there was another proposition which was, instead of maximizing the explained variability, we want to find a subspace that minimizes the unexplained variance. So we want to, well, actually explain the maximum information. So since we're measuring things in terms of variance, we want to have the subspace that minimizes the sum of square of the residues. Okay? So this can be done if we have a subspace on manifolds. So what's the type of subspaces that was considered is you take a point, tangent vectors, and that is generating with geodesic, that is generating some kind of subspace, which is totally geodesic at this point, but which can be, well, non-geodesic, well, non-well behaved when you go a bit farther away. And then you try to minimize the projection error. So this is still, so here the idea is really that we don't want to make assumption about what is the distribution within the subspace. We just want to find the subspace that fit the data and then postpone the analysis inside the subspace later. So we just have the idea that we have a Gaussian noise or something like that on the unexplained direction. Okay, all these methods are intrinsically linked to the fact that we have a subspace which is defined around a point. So it means that if we have this example where we have data on the equator and the mean value is here, well, if your mean point is not within the data, then it's not going to work very well. Or if you have this type of distributions with bimodal distribution, well, the mean point that optimally describes all the data is somehow in the middle. So that's one of the problems of this type of definition. So there has been other type of extensions. So I will not cite them all because of the time, which is running quite a lot. I'm just going to show quite quickly one of the ideas that we have developed recently, which is to try to define, to generalize the affine span in manifolds. And the idea is that in a Euclidean space, we can rephrase the affine span at different points of k plus 1 plus 1 point as the set of points x such that this equation, this barycentric equation, is 0. So basically what this means is that if you are at x and you look at all the data points, and you weight that with some weights lambda, then you can find a linear combination which is 0. Okay? So this looks like a weighted mean. So this is exactly the idea. Define the locus of weighted mean as define our subspace as the locus of weighted mean. Now we have different definition of the means. We have the Fréchet mean, we have the Karcher mean, we have the exponential barycenters. So the first two, we can consider the weighted variance. So this is this criterion. And the local or global minima of that functional are called the Fréchet. Well, Fréchet is global, Fréchet and Karcher. Fréchet is global, Fréchet and Karcher barycentric subspaces. And one of the interesting things is that this is still working in spaces which are stratified. If you take several pages of a book, you can take a point on a page, a point on the other page, and you can go through singularities. So this is one of the interesting aspects of that definition. And the exponential barycenter definition is basically this one. If you are at a point of the manifold where when you shoot to the reference points you can find a linear combination, you are within your subspace. So this is a kind of, equation is kind of a matrix equation on the tangent space at each point, and we're finding the 0 of that. Okay, and the last definition is this is working only if this is defined, so this is not working at the cut locus of reference points, so the affine span will be the completion of that space. So of course there's a lot of questions, and I will try to answer just a few. So under some assumptions, in particular that the fact that the points are linearly independent, we can show that these spaces, they are well behaved, at least around the points, the reference points. And if the points are sufficiently concentrated, sufficiently in the sense of the theorem of Kendall, then within the ball where the Karcher and Kendall Karcher and Fréchet mean were unique, we have uniqueness of the space which is generated. Now, if we reformalize the equation of the exponential barycenter using this matrix equation, where this is just at each point the set of vectors pointing to the reference points, the set of the logs. We do a singular value decomposition, and we can see that the exponential barycentric subspace is the 0 level set of the 0 singular values. And we can have a stratification with the number of singular values. So we can try to investigate the relationship between the different subspaces. The obvious thing is local minima are, global minima are local minima, and local minima are critical points. So outside the cut locus, we have a clear inclusion property, and we can go one step further. We can try to look at what is the Hessian matrix to see what are if it's a local minimum, saddle point, or local maximum. And so actually what's happening is if we look at the Hessian matrix, the weighted Hessian matrix of the square distance in the exponential barycentric subspace, it defines a map. If we look at the index, it defines a map where we have regions where we have local minima, regions where we have saddle points, regions where we have local maxima. And this is an example of what it gives on the sphere. So here, the points in red are the antipodal points to the reference points. So we have 3 points that we can't see on the back. And here we have 2 positive eigenvalues, saddle points in blue, and local extrema of the weighted variance in green. So actually, this would be in brown, this would be the Karcher barycentric subspace. So in terms of definition of subspaces, it might not be the best definition. It's better in the sphere. The exponential barycentric subspace is the full subsphere except the cut locus, and in the fine span we find them again. Okay, so that's now I'm arriving to the perspective and the open problems. So there's a few first perspective on the barycentric subspaces. So one first thing is to try to generalize that with other types of distances, the alpha distances that we have when we put the power, a different power in the metric. That is not changing anything. We define exactly the same subspaces. So the affine span with the if we take the alpha power of the distance is the same. So it's an unexpected stability result. So now the other thing which would be very interesting is what's happening where points are approaching from one another. So if we take 2 points, if they are coalescing, then they will define a one jet, a point with a tangent vector. If we take 3 points, they will define, if they converge at the same point with different tangent vector, they will define a point and a subspace of the tangent space. So what we can show is if all the points converge to the same point at the first order with different tangent vector, we're converging towards the geodesic subspaces that were used before. Now, if they converge at different points, at different locations, they will generate different non-local jets, and it would be interesting to be able to show what are these spaces. And my conjecture is that it could be a way to define actually splines on manifolds, and it could converge towards splines. So that's a conjecture which is open. Okay, the second thing which is interesting would be, this is a definition which is driven from, statistical need, but is there a variational formulation that could handle the global picture of that submanifolds? That is also an open question. The second thing is, so far I talked about PCA, but PCA, when you do a PCA, you're computing the mean, the first mode, second mode, third mode, and each time you're building an increasing sequence of subspaces where your data are better approximated. So what we would like in manifold is actually not just find one subspace of fixed dimension, but a series of embedded subspaces. So with the barycentric subspaces, we can do that with adding points. But if we just do that, adding points one at a time, this is not optimal. So we can design, can we design criterion that are optimal? Well, there is at least one criterion which is doing that, and that's what I call barycentric subspace analysis. So more generally, what are the open questions? The first one is, well, obviously more advanced statistics, Cramer-Rao bounds, central limit theorem, what is the efficiency of the estimation, especially for the application in medicine with a finite number of points. So central limit is good when we know that it's Gaussian with a very large number of points, but if we have 10 subjects or 20, then it's not infinite. So what's the effect of curvature on that? So which metric? That's a very, very huge problem. So Alain tried to draw a picture of how we can find interesting metrics for our spaces, but that's a key feature because any least square, when we are minimizing the distance, somehow we're assuming that the noise is isotropic. So choosing the distance is absolutely the key. Then how to deal with completeness issues when the manifold is not complete. Or if we take the metric completion, then we can't have geodesic completeness. So how to handle that in the statistical setting. How to add also other things like gluing other manifolds, like trees. That's a big question. Although there seems to be quite interesting results, like the log map is well defined on the set of trees, and we can use that to actually do part of the algorithm that we have here. How to go to bundles and quotient spaces. And here I just want to show one example of recent work. If you take the set of 2 points, so actually 1 point and you quotient out by rotation. So, and you add noise in the ambient space. So let's assume that you have this point in the quotient space. You take 3 realization of this point and you add noise in the tangent space. So what we do usually is we project, we project everything in the quotient space, and then we take the Fréchet mean in the quotient space. So in this case, the induced distance in the quotient space is the Euclidean one. Okay, the problem is, because you see here that there is more mass on this side of the circle than on this side, you have actually a bias. So taking the Fréchet mean in the quotient space when there is noise in the top space can induce a bias. And we can actually quantify the importance of this bias with the extrinsic curvature of the orbit of the template with respect to the noise. So this is the type of some types of results that we are trying to establish right now, and here are a few extension of reference to extensions that are very recently appeared, in particular with the work of Loïc de Villiers that we advise with Stephanie and Alain. So there's also results in infinite dimension showing that this bias exists. So that's one of the things that we need to think now. If we have data in the in a shape space, but if we measure them in the embedding space, and if the noise is there, then we have to take into account how this is interacting. Okay, so I'll finish that there. Late. And maybe if there's very short question, then we can take them now. Otherwise, maybe we go to the next talk. Yes. Yeah.
No, just some historical remarks. You have a paper of Hermann Karcher of 2013.
That's the one that I cited for the arguing of the naming.
He makes comments on Wikipedia where they talk about Fréchet mean and Karcher mean, and he say, yes, Karcher means are a closely related construction named after Hermann Karcher, and Karcher write, who believes that Fréchet would have been proud of this naming. So I assume that he proposed to call it.
So we're actually our convention is to keep what Fréchet proposed, which is the global minimum. And so we are naming the local minima after Karcher.
But I think the idea is 100 years ago, 100 years before Fréchet, in the lecture on probability by Antoine Augustin Cournot, you have some discussion about, so he gives the example of right triangle, on how to make statistic on right triangle, and also they deals with l'homme moyen, so how to make statistic on size and weights, because they are correlated. So you have this idea of, which has been introduced after, on just a technical question, classically, when you have extreme value statistic, so Gaussian model or maximum entropy model are not sufficient. So in this case, we have to use non-parametric density estimation.
So there is also some work on non-parametric density estimation on manifold, in particular by Bruno Pelletier, and there's quite a few works after that. So this is also based exactly on the same principle that you're trying to minimize the weighted distance to a number of, to your data. That's how the density is built. So it's the same principle which are used to that. So this is a way, and the other way is also to build some Bayesian estimation, and maybe Stanley will talk about that tomorrow.
Because they are using also statistical depth, so I don't know if you have looked at that.
Yeah, I looked at that, but it's quite, it's interesting, but how to generalize that to manifolds. So there's quite a few interesting things to generalize. The whole point is, how can we rephrase that in general manifolds, not only the negatively curved ones, or manifolds. So that's where things are branching. Statistical depth is an interesting notion, not yet generalized from what I know to manifolds.